Hello everyone, I'm glad to present the work Occupancy Grid Map Estimation based on visual SLAM and ground segmentation. Regarding autonomous mobile robots, it is possible to highlight three aspects: perception on mapping, location, and navigation. A powerful ally for more robotics autonomy is the SLAM algorithms, representing an intersection of mapping and location. Among visual SLAM classifications, the feature-based method associated with a sparse mapping gives a real-time system which is capable of detecting loop closure and doing optimizations both in real time. All of this combined with accurate location data. But concerning the mapping stage, the sparse point cloud represents a disadvantage for navigation tasks. Based on that, our proposed solution consists of a module that allows a link between this visual SLAM and navigation tasks, prioritizing low computational costs both for memory and performance. We propose this link by transforming the sparse mapping into a 2D occupancy grid map. The related works can be divided into two categories, which are works that developed an appropriated map for navigation given a sparse point cloud, and a second category that uses a dense point cloud. For now, I will focus on a particular one, which is the open source project RTab map, used for comparative purpose. It can build a 2D OGM with data from a stereo or RGBD camera. Specifically about the 2D OGM generation, the dense point cloud is divided into voxels, and for each one, a plane fitting is performed. Given the plane's tilt angle, the voxel is classified as a free or occupied area, followed by its projection into the 2D grids. Additionally, a ray tracing option can complement the map. Our approach uses a similar flow. However, instead of using a dense point cloud, we directly use the sparse point cloud generated by the SLAM system, resulting in a reduced processing time and memory usage. Another main difference is that our approach defines free area based on a two-dimensional search, avoiding three-dimensional data computation. Here, we can see the workflow of our proposal. Initially, images and camera parameters are inserted into the feature-based SLAM. We adopted the open source project called OpenVSLAM to provide location and mapping. An image frame is only putted in the image segmentation module if the SLAM system defines a new keyframe. Subsequently, the entire sparse point cloud and the segmented image go to the cloud segmentation module. Lastly, the 2D OGM generation module receives the segmented cloud, the keyframes pose estimation, and the keyframes features in pixel coordinates and their respective 3D coordinates. To achieve a segmented image, first, we calculate a disparity map using the same global mapping technique and its respective V and U disparity map. V disparity concerns a histogram based on the lines of the disparity map, while U disparity considers the columns of the disparity map. They review obstacles as horizontal lines and the longitudinal profile of the free area, as shown in the figure at the top. Next, it is necessary to filter the V-disparity map. This is, remove every dot not related to the ground. The filtered V-disparity map is modeled by B-splines curves, in our case a combination of 5 cubic splines, each for 5 segments of the V-disparity image, as shown in the image. And parameters are estimated by the least square method. Finally, the image segmentation is completed by verifying every pixel of the disparity map D. If a pixel AJ belongs to the model B-spline function at J, then pixel is categorized as free area, otherwise as an occupied area. Once we have a segmented image, we can extend the segmentation to the 3D point cloud data. Feature and the respective 3D point located at the free area are defined as floor, otherwise as non-floor. The segmented point cloud is updated whenever a new keyframe is inserted into the SLAM system, which is the moment that new points are added or removed to the cloud. At this point, we have the sparse point cloud from the SLAM system, the segmented image, and the segmented point cloud between ground and non-ground. The entire non-ground point cloud is used to form the first OGM layer, which indicates only occupied area. Among the ground points, each point observed by the current keyframe form with the current pose estimation a line, represented by a distance value. We assume the set of distance value follows a normal distribution. Thus, outlier removal is performed based on a superior threshold calculated as shown in the equation. The remaining ground points are used to apply ray tracing projected into a secondary OGM. This is a layer containing only potential free grids. The final map is resulted from overlapping the two layers, and in case of conflict, the obstacle grid prevails for the sake of security. For evaluation purposes, we recorded 3 real environment scenes and a large synthetic one, as illustrated in the pictures. In 3 of them, we extracted the map ground truth. This is the configuration we used to compare our method, SegFloor, and RTab map. It is inputted for both the odometry data from OpenVisLAM, the image pair from a stereo camera, the robot frame transformation, and camera parameters. To our strategy, we also input the sparse point cloud from the OpenVisLAM. You can also see a brief overflow of each strategy. For those scenes with ground truth, here are the results of maps overlay. The area highlighted in pink represents incompatibility between generated and ground truth maps. Therefore, the less pink color appears, the better the map quality. Maps from SegFloor and RTab map with the ray tracing option demonstrate a big intersection in most navigable areas. In Hall 1, the passage was noticed. In Hall 2, the obstacle was detected. In a synthetic environment, pilasters and other objects were also detected. For these environments, it was possible to calculate precision and recall using a probabilistic roadmap. Precision metrics are calculated by comparing the probabilistic roadmap generated over the estimated map and replicated on the ground truth. The table brings high values for the map's precision for both strategies. This is expected when visualizing the maps overlaid, given that most of the free areas coincides. In this way, collisions are hardly expected. We also use the recall matrix to define how much of this estimated free area represents the entire free area of the ground truth. This is, the recall represents map coverage. It is calculated by comparing the probabilistic roadmap generated over the ground truth and then overlaid over the estimated map. Again, the table shows high and competitive results between SegFloor and RTab map. The synthetic environment has an area of almost 700 square meters and a trajectory of 138 meters. It was also used to validate our technique in long term. The figure on the left reports the memory footprint over the number of map updates. It is interesting to note that using OpenVisLAN associated with RTab map is practically equivalent of having 2 SLAM systems running in terms of memory consumption. On the other hand, changing this configuration to OpenVisLAN followed by our proposal represents slight offset regarding the SLAM's memory footprint. Regarding the processing time over map updates in the figure on the right, the trend lines highlights an almost constant behavior of our approach and an increased behavior of RTab map. Regarding the remaining scene without a map ground truth, you can see the resulted map from both SegFloor and RTab map, where some elements are indicated. Through this scene, we want to highlight the cost of the point cloud optimization once a loop closure is detected. While our segmented point cloud is optimized in 37 seconds, for RTab map, the optimization of its dense point cloud costed almost 10 times more than our proposal. Here, you can watch a demo video of our application. This scene is regarding Hall 1, with a narrow passage. Besides the 2D OGM generation, you can also visualize the segmented point cloud. This other scene is regarding Hall 2, with an obstacle. Here, It is a more complex scene with various elements, varying from size and textures. Lastly, you can watch an extra scene recorded in an off-road environment. We conclude that the proposed technique actuates as an extension of the mapping stage of a feature-based visual SLAM, representing a link between the space point cloud and navigation activities. Tests made in both synthetic and real environment achieved a high accuracy map and good coverage. Besides, the method requires a low memory and low cost consumption, even for large scenes. Limitations consist of scenes in which navigable areas have no textures. Our main perspectives consist of IMU integration for a better camera pose estimation and extension of the binary map to a probabilistic context, a more suitable representation for merging maps generated by other sensors. Furthermore, to achieve even more computational optimization, integrating our technique in an embedded stereo vision system is a valid strategy that can also help with low energy consumption. Thanks for your attention and please check out our paper.